now we should go to the 10 or 5 minutes for the question and answers. Anyone?
For John and Roy, yeah, you showed both some conservatism with wind speed and height, and that was good. And so the question is there any conservatism with return periods, and what do you think is reasonable and unreasonable based upon your experience?
In terms of ultimate, I think we've moved to at least an ASCE 7, and it's starting to make its way around the world. Explicit consideration of what is considered, at least among some, me included, to be a more rational examination of what the ultimate event is. So is that event for a very important building somewhere between 1,500 and 2,000 years? I think that's a sensible number in my estimation, at least, given the importance of the buildings that we typically get into. I think it's a different question for the vast majority of the building stock, which could probably, I think, as we see how it performs in windstorms and natural disasters, generally they may benefit from a little bit better consideration of the ultimate event. When we look at serviceability, Roy made some good comments on building motion and its perception, and I think there's starting to at least among the wind engineering community, starting to get some agreement on looking at a more frequent event. A lot of design is focused on the 10-year acceleration. That was a product of, actually I think it arrived in building codes in the National Building Code of Canada when serviceability design was done at 10 years period, and there was no discussion. So moving towards a more frequent event, I think, is a benefit for serviceability considerations.
Yeah, I guess I would agree with John that the couple other things that we do need to think about a little bit is our overall structural reliability for strength. We're going out to this longer return period that appears to be reasonably consistent with sort of life safety goals. But when we do that, in a lot of places we're moving towards probably greater degrees of uncertainty in our prediction of what the wind speeds will be out of those regions. We're moving into greater degrees of uncertainty about exactly what the dynamic characteristics of the building will be at that kind of level of amplitude that you would expect there, where there's going to be significant damage and cracking. We haven't yet looked at the relative reliability of the different building components enough. So if you take a lot of the sort of your fully glazed, clad, super tall buildings, the chances are that in that kind of a windstorm, your cladding may well be the weak point. And if you start losing cladding from your building, which can happen if a neighboring building starts losing its cladding, debris starts flying, there tends to be a bit of a significant loss of building envelope. The nice part of that is that when that happens, most of your crosswind response is probably going to disappear because you've broken up the vortex shedding through actual damage to the building. On the serviceability stuff, we are definitely, I think, worldwide moving to a short return period for the accelerations. The key thing that probably not enough people appreciate is we tend to look at adding supplementary damping to buildings. And we say, look, this is what it'll do to the 5-year expected acceleration. This is what it'll do to the 1 year. The key thing that the damping does in a tall building, the supplementary damping, is it reduces the frequency of occurrence of perceptible motion. So rather, you've popped the damping up a little bit, you've maybe brought your 5-year accelerations, your 10-year accelerations down by 30%, but you might have moved the building motion from being perceptible once every 3 weeks to every 3 months. And that's the real one that causes a significant improvement and makes your occupants a lot happier.
I want to apologize. My question is going to last 1 3/4 of a minute more than expected. I first want to mention that I've enjoyed very much the whole 3 lectures. And my questions might be addressed to any of the distinguished speakers, including the amazing Scottish accent of Roy. I'm a civil engineer, but I'm also an aeronautical engineer, quite weird. And in my office, my own office, we're doing both structural engineering in civil engineers, but also we're designing flight vehicles. Working in such an interdisciplinary environment, you sometimes find yourself in a peculiar position where you find that very simple ideas in one field are not even considered in the other. In aeronautics, we are looking for maintaining lift, usually. And in structure, in civil engineering, we are looking on reduction of wind loads. But in both cases, we are looking for a reduction or even diminishing vortex sheddings and whirls of all types. I want to mention two devices that we are using in aeronautics, and I want to ask you if it is considered in using in civil engineering. These are day-by-day devices that we are using in aeronautics. One is called slats. These are sort of control surfaces that are laid in front of the leading edge of the wing, and it moves on rails. You open it in order to create a slot between these two surfaces, the upfront going slat and the surface of the wing. And then the flow that goes in between somehow glues the upwash or downwash or whatever to the upper surface of the wing and maintain lift by reducing whirls and separations. The other is called vortex generators. These are small tabs that we are gluing on top of the surface. They raise energy by whirling the flow over the surface, and also they reduce dramatically separations and whirls of any type. So I've seen many slots here in the lectures, but somehow they were related to energy conservation and usage for some other green type of engineering. So I want to ask you if you can refer to these devices. Are they considered in using in buildings? Thank you.
I think the easy answer to that is yes and no. And while we will quite frequently use little aerodynamic modifications, like your vortex, your generators on top of your wings, we have to be careful where we use them. For most of what we're doing, we're driven by separation from sharp edges on the building, which is causing the vortex shedding. So the bluffability aerodynamics part of it. Occasionally, I mean, you saw the example where I was taking some measurements up a mast. Those masts were moving a bit too much. It was visible from the ground. And we actually retrofitted some turning vanes just in the corner to control that. It was a nice aerodynamic add-on solution of the type you're suggesting, and the passive type of solution. In terms of active solutions on buildings, I think we'd be struggling to find developers and probably many structural engineers who are actually happy sticking in sort of active aerodynamic modifications to buildings at the moment. Because there's obviously a cost element with it, there's a risk element if it doesn't work. So yeah, I think we're away from that at the moment. John?
Yeah, I would certainly agree with that last comment. I mean, we'd certainly look to passive solutions not only because of the economic and risk considerations, but they're reliable. But on the slots issue, we've worked on several buildings where we've introduced slots at the corner, and in one particular case, we reduced the accelerations and the loads by about a factor of about 2.5. So that is often something that we look to. It takes a certain type of building or a certain type of geometry to benefit that. And in fact, the example I showed, Adrian's building, the Wuhan Greenland Center, that was something that we introduced towards the top of the building.
Well, just wanted to add that, yeah, I mean, there is a little bit of difference, obviously, between the flow that you're dealing with and the flow that we're dealing here. I mean, there's quite a lot of turbulence in what we're doing, and that makes things a little bit different in terms of the way we manage the response. But, yeah, I would say that in general, the introduction of, you know, purposely designed modification, especially around critical areas, as Roy and John were saying, can actually lead to you know, quite good savings. Now, obviously, those needs to be tuned specifically for the type of period and the type of width and dimension that they're actually dealing with.
Yes, just off-the-wall question. I'm Mark Garland from Toronto. We're like the high-rise condominium capital of North America. And the city's just waking up to balcony guards and divider screens. And so like these buildings are, you know, 20 to 40, 50 stories tall. And the residents like their balconies. And so you've got a 6-foot divider screen that separates the two suites. And then you got the glass balcony guard at the outside edge of the building. And the buildings that are, say, 5 years old, I'm not aware that they used any wind loading in the design of those balcony guards and divider screens, and some of the older buildings are flapping around. And what should the architects or specifiers be doing relative to the wind load on those components in the building?
Well, I'm closest to Toronto, maybe I'll take that first. Wind loads on balconies is certainly something that we can derive and do derive from wind engineering studies. Now, some of the older buildings that you mentioned, or maybe some of the shorter buildings, didn't go through that level of testing. So I can't comment on what loads may or may not have been considered, but it is certainly something that we do look at when we're looking at curtain wall testing. Now, I know that that specific issue in Toronto is as much a material issue as well. So there's
not talking about the glass.
Okay, but nonetheless, there is a level of testing that certainly we carry out on a regular basis when we're looking at tall condominium towers to look at pressures on those elements that you mentioned.
Would the wind load on those components be the same as on the curtain wall glass?
Often, no. No, we measure the differential load across those elements, specifically at you know, areas where we expect them to be particularly sensitive.
But on a 30-story building, nobody's prescribing what to do.
That very well may be, because 30-story buildings often don't, it's not judged a prudent use of a developer's dollar.
Well, then the poor subcontractor just makes it up. The connections.
Yeah, that's, I mean, we're getting into a pretty lengthy discussion. Anyway, I don't know if any of the other guys will comment.
Not really a comment, but to kind of bring it back a little to sort of the theme of the talks, which was more sort of based around response. It's quite interesting looking at some of the condos down in Florida where they have the hurricane shutters around the outside of the balcony, because the response of the buildings changes significantly depending on whether those hurricane shutters are open or closed. So it's one of the cases where we actually need to look at both, and you need to look at the overall response of the building with them closed for your extreme event and some of the more regularly occurring things, your design pressures on your balconies and components for the more regular winds. So.
I'm sorry. Oh, last question, yeah.
I don't have a question. I just want to comment. I appreciate the technologies which was discussed here, and they're all coming from the wind tunnel perspective. But I think we should be aware that similarly, the strides are being made in computational aspects where the shape optimization of buildings can be done based on basic principles of fluid mechanics, and you don't have to tell what to change. You just prescribe the constraint, and it will be done like it has been done in aerospace industry for the aerofoil, which is much simpler than in our case. At the same time, to go one step beyond, you could do the topology optimization of the structural system, which couples and provides you the best structural system for the shape you have optimized. These are still in the development stages, but hopefully soon as the computational power improves, this will be a supplementary approach to do what you guys are doing, and perhaps faster.
I'll just make a comment here, Hassan. Stefano mentioned some of the work that they've been doing on workshop, and Roy mentioned that his, in the morning he was able to develop the data that he presented here. I think in parallel to the strides that we're making with CFD, we're making a lot of efficiency gains within the wind tunnel. And the wind tunnel technology has not remained static over the last 20 years either. And we've made a lot of progress, I think, within the community in how to apply the existing technology much better into design. So I certainly commend all the developments in CFD, but I would just say that there's equivalent developments that have been taking place in the wind tunnel.
Thank you all.